So today we're going to start talking about color. So we're still talking about light. We're still talking about the EM spectrum. We're just talking about the visible part right there in the middle of the spectrum. And the overarching idea, what we're going to be looking at is color by reflection and color by transmission and color mixing. So right here you're looking at the color wheel. If you look here, you have a red circle, a blue circle, and a green circle. And it's not exactly like you were taught in art class. When you mix colors of light, you're actually adding light waves together. You're getting an interference pattern. You're mixing different frequencies and wavelengths. So here, when you mix red and green, you get yellow. When you mix red and blue, you get magenta. When you mix blue and green, you get cyan. When you mix blue, red, and green together, you get white light. So remember in art class, if you mix blue, green, and red together, you get brown or black, the absence of color. That's because you're subtracting. Each color is subtracting a little bit of color, is absorbing it. When you add light waves together, you're not subtracting anything, you're actually adding. So our primary colors are red, green, and blue, and our secondary colors are magenta, yellow, and cyan, and then white is the mixture of all three colors.
Eureka! The story so far. One of the chief ways in which heat energy moves is in the form of waves. Sources of heat, such as the sun, or a fire, or a stove, send out these waves in all directions, as if each wave were the spoke, or to use the Latin word, the radius of a wheel. This is why this third kind of heat transfer is called radiation. And now, the radiation spectrum. In warm weather, you seem to feel hotter if you're wearing black than if you're wearing white. Is this just your imagination, or are black things really warmer than white things? What could color have to do with heat? What is color anyway? Why are tomatoes red? Or oranges orange? Or buttercups yellow? Or green peas green? Or blueberries blue? Or violets violet? Where do all these colors come from? They come from light itself. White light contains all the colors. See for yourself. Go into a dark room. Open a chink in the blinds and let a narrow beam of light in. Now hold a glass prism in the light beam. Look at the colors. Red, orange, yellow, green, blue, violet. That's what white light's made of. When it shines all these colors on a tomato, the tomato absorbs each of the colors, except red, which it reflects. That's why tomatoes look red. Oranges do the same. They absorb all the colors, except orange, which they reflect. So oranges look orange. Buttercups only reflect yellow, so they look yellow. The same thing applies to green peas, blueberries, and violets. Now, if you mix all these colors together again, you get white light once more, because white is simply a combination of all the colors. Your white suit appears white because it doesn't absorb any of the colors. It reflects them all. On the other hand, your black suit appears black because it absorbs all the colors. It doesn't reflect any of them. Black is simply the absence of any color. But what's all this got to do with black being warm and white being cool? Well, when the sun radiates waves of heat energy, these waves come in many different forms, which make up a whole band or spectrum of energy waves, from radio waves at one end to X-rays and gamma rays at the other. Some of this heat energy is visible. These are the light waves made up of all the different colors. But these only take up a little bit of the radiation spectrum. The rest of the spectrum isn't visible at all. There is, for example, some invisible radiation just beyond or beneath the red. Since the Latin word for beneath is infra, this is called infrared radiation. Now, most of the sun's radiant heat energy comes to us in the visible and the infrared parts of the spectrum. And that's why black is warm, because it not only absorbs the heat energy of the visible colors, but in doing so, it also tends to absorb a lot of the heat energy of the invisible infrared radiation as well. Conversely, white is cool, because it not only reflects the heat energy of the visible colors, but in doing so, it also tends to reflect a lot of the heat energy of the invisible infrared radiation. So now you know that color really does have something to do with heat. It isn't just your imagination. You also know what lies at the end of the rainbow. It isn't a pot of gold. It's infrared radiation.
Science, please! The wonderful world of color. There's no such thing as color. We live in a colorless world. Color is an effect produced in our eyes and brains by light. White light consists of different lengths of light waves. Each wavelength produces a different color sensation. A banana looks yellow because its surface absorbs all wavelengths except yellow, which is reflected back to our eyes. In the same way, a cherry looks red because its skin absorbs all colors except red. And vanilla ice cream gives the illusion of being white because it reflects all wavelengths of light. So, color doesn't really exist, but it does have a very real effect on us.
Okay, so the key here is, for all of this, is that we have three primary colors of light: red, blue, and green. And when they're mixed together, again, you can see from the color wheel where the green and the blue mix, they make cyan. Where the red and the blue mix, it makes magenta. Where red and green mix, it makes yellow. And where all three colors mix, it makes white. Okay, so we have additive and subtractive primary colors. So our primary additive colors are red, blue, and green. And if you add all three colors of light together, you get white light. If you add red and green, you get yellow. Blue and green, you get cyan. And red and blue, you get magenta. And if you pay attention to, like, your printer, if you've ever had to change the color, the ink cartridges, your printer always has black ink, and then it always has yellow, cyan, and magenta. It always has the secondary colors, because you can, when you spray printer ink onto a paper, what you're doing is subtracting different colors of light. Talk about this more when we do our color filter lab and our light mixing lab when you're in class. But we have our additive primary colors and our subtractive secondary colors. These are a little different than they are in art class. So colors by reflection. Objects are the color of the light that they reflect. So, like here's a red object, red sheet of paper. White light is actually made up of red, green, and blue, or the whole rainbow. You only need these three colors. And this paper appears to be red because the pigments or dyes in this paper absorb blue and green and reflect red. So this paper is red because it reflects red to your eyes. Okay? If there were only green light available, this red sheet of paper would not appear red, it would appear black, because remember, anything red absorbs blue and green and reflects red. So if only green light is available, there's no red light to reflect, so the paper would appear black. Person would not see it. Red sheet of paper, if yellow light is available, and remember from our color wheel, yellow is a combination of red and green. And this red object, this red piece of paper, absorbs blue and green and reflects red. So if your red sheet of paper were illuminated by only yellow light, well, it would still look red because there is red light in the yellow light. Okay, and here's a cyan object, a cyan piece of paper. If white light is available, that means red, blue, and green is available, and the cyan object is cyan because it reflects the blue and the green. If it just reflected blue, it would be a blue object. If it just reflected green, it would be a green object. But it reflects blue and green, and when your eye picks up blue and green wavelengths of light at the same time, your brain makes up the color cyan, and the red light is absorbed. Okay, same cyan piece of paper. If magenta light is available, remember magenta is red and blue mixed together, well, this cyan object reflects blue and green as long as there's blue and green light available and absorbs red. So the red gets absorbed, the blue gets reflected, so the paper would look blue in magenta light, because there is no green light to reflect to make it cyan. So again, objects are the color they are because of the light that is available and the color that they reflect. Okay, so real quick here, red objects reflect red light. Yellow objects reflect yellow light. Black objects, black objects absorb all colors. So they don't reflect anything to your eyes, that's why they look black. White objects reflect all colors and absorb none of them. So when all colors are reflected to your eyes, your brain sees red, green, blue, and creates white out of it. Okay, and now we're going to talk about color by transmission, which is not color bouncing off of things, but color passing through objects, like filters. Okay, and here is a cyan filter. If white light is available, that means red, blue, and green is all available. The cyan object, or transparent cyan object, appears cyan because it absorbs red and lets blue and green pass. And blue and green is cyan. Your brain makes up this color called cyan when it sees blue and green together. If white light is incident upon a red transparent object, the blue and the green will get absorbed and the red will pass through. So the object is red because it allows red light to pass through and absorbs the blue and green. A blue object is blue, or a blue transparent object allows blue light to pass and absorbs red and green. A yellow transparent object would allow red and green to pass and absorb the blue. So it's like yellow objects reflect red and green. Well, transparent, like yellow glass or yellow plastic, allow red and green light to pass through. Magenta filters will allow red and blue light to pass and will absorb the green. Okay. So here we're stacking up filters. So here is, if we have white light that is passing through a red and a blue filter, you just have to think of them one at a time, and it doesn't matter which order. But the red filter would absorb the blue and green and let the red pass. But the blue filter, it would be blue because it absorbs red and green and lets blue pass. In this case, there is no blue to pass through. There's only red light incident on the blue filter, so the red light gets absorbed, and the person's brain sees no light and says it's black. So in the bottom, we have white light, so red, blue, and green, hitting a yellow filter. Well, yellow is a combination of red and green, so red and green passes, the blue gets absorbed. The magenta filter absorbs green, lets blue and red pass. There's only red available, so when you stack red and magenta, your brain sees red.